Morning, guys. Happy Monday. Um, it's miserable weather out, but we'll get through. Anyway, part 10. Welcome to part 10 of chapter 9. And today we're going to talk about exchange symmetry. So as of now, we have a set of four quantum numbers. We have n, l, m sub l, and m sub s. And if we incorporate spin orbit coupling, then the four quantum numbers can become n, l, j, and m sub j. So sometimes these are the best, and oftentimes these might be the best. So depends on the problem, depends on the questions being asked. So one question that we could ask ourselves is how many electrons can have the same four quantum numbers. Now, interestingly enough, all of you have taken general chemistry at some point, and you were told that no two electrons can have the same four quantum numbers. And you were told at that time that was the Pauli exclusion principle, but that was just the statement. It wasn't at all a proof. And so I'm going to offer up a proof for that today. And the Pauli exclusion principle is due to Wolfgang Pauli. In my top 5 physicists of all time. And he did this in 1925, shortly after Schrödinger. Did his thing. So things happened really quickly after 1925. Things were happening quickly between 1900 and 1925, but there was an avalanche of physics occurring after Schrödinger and Heisenberg worked on their quantum mechanics. So we have then from Pauli, we have the Pauli exclusion principle. Oops. Right, the Pauli exclusion principle. And so let's see how that comes about. So, and again, to put the cart in front of the horse, right? So this comes about because electrons are indistinguishable. Electrons are indistinguishable. And sometimes we say that these are then identical particles. And let me help you a little bit with that notion. So let's take a look at an electron-electron collision. And so imagine we have an electron here and an electron here, and they're going to collide. Glancing collision, it's not a head-on collision, and so this electron's going to come in here, and this electron's going to come in here, and they're going to quote-unquote collide, right? They probably are not going to physically touch, right, because of the electrostatic repulsion, right? So they're going to quote unquote scatter by way of the electromagnetic force, and so we see that an electron emerges here, and through some angle theta, we see that an electron emerges here. Okay. And again, this would be an electron here. And let's think about this. This can also have another way of looking at this, right? So this electron's going to go this way, right? This electron's going to go this way. And what might very well happen is that this electron might actually veer off in this direction. This electron might veer off in this direction. And the bottom line is that we can't tell for sure which one of these events actually took place. Okay, and so the bottom line here is that during this process, when they get very, very close, right, we can't tease that apart. And again, that's due to some Heisenberg uncertainty relationships. So the bottom line is that identical particles cannot be told apart in any way, right? And that's a bold statement in your text and probably worth jotting down, right? So identical particles cannot be told apart in any way, i.e., they're indistinguishable. Okay, beautiful. So up to now, we've been pretty much been looking at the hydrogen atom, but let's see what happens when we look at a multi-electron system, right? So we're gonna look at helium, which is a 2-electron system. It's our first look at a system that has more than one electron. And so let's get a picture going here. So we have our helium nucleus. Which is going to have 2 protons, 2 neutrons. Right, so it's got a charge of positive 2e. And then we're going to have a couple of electrons, right? So we have electron here at some distance r1 at some instant in time. We have an electron here at r2 at some instant in time. And we have the inter-electron distance, which is going to be r1 minus r2. Okay, so there's our picture, and there it is at some instant in time. And so if we neglect one electron at a time, we can write down the Hamiltonian, right? So remember the Hamiltonian is the kinetic plus the potential energy. And so for electron 1, we would have negative h bar squared over 2m. We'd have del squared of electron 1 operating on the wave function plus a negative 2e times e. That'd be 1 over 4 pi epsilon 0 over r times psi. And then we can write the Hamiltonian down for the second electron, just minus h bar squared over 2m del squared operating on psi plus 1 over 4 pi epsilon 0 negative 2e times e over r operating on psi. So what we're not going to talk about, right, since there's another interaction here, is we're not going to talk about the interaction between the two electrons. And so if we were to write that down, I'm going to write this as VEE, and that's going to be 1 over 4 pi epsilon 0. It's going to be E squared over the magnitude of R1 minus R2, right? Because the only thing that matters here is the distance between them. So this is the electron potential energy. And for reasons that I don't want to go into right now, putting this term in makes this problem intractable, and it's not able to be solved in a closed analytic form like we were able to do with the hydrogen atom. So neglecting this, right, so we're going to neglect this, and we'll deal then just with these two one-particle Hamiltonians. And so we say that this is the independent particle, the independent particle approximation. Independent particle approximation. Again, because it neglects the electron-electron interaction term. So then we could write the Schrödinger, right? We can write the time-independent Schrödinger equation as, and again, we'll just call this then H1. We'll call this H2, right? Where H1 and H2 are the Hamiltonians for particle 1 and particle 2, respectively. So this is going to be then H particle 1 operating on psi plus h particle 2 operating on psi. And that's going to be equal to E psi. And I've adopted the same notation as in your textbook, so you won't get confused in lecture as opposed to reading the text, which I hope you're doing. So we need an ansatz, right, for the solution for this, and the ansatz is then that clearly psi is going to be some function of R1 and R2. All right? And clearly, then, the absolute value of psi R1, R2 squared is going to represent the probability of finding one electron at R1 and the other electron at R2 at a given time, right? At a given time. Now, indistinguishability ensures that a formal interchange of particles, in this case electrons, produces no observable effects. What that means is we can merely take the particle at R1, interchange it with particle at R2, and there should be no observable effects on the system. So I'd like to end right there because the next part is going to introduce what is called the exchange operator, which is not in your textbook, and so that's going to take me a little bit of time to develop. So I'm going to end this lecture right here, and we'll pick up with part 11. Have a good morning, guys.